Hello everyone. In this lecture we're going to introduce a few of the other common charts used in statistical process control. The X charts for individuals, moving average and moving range charts, and the exponentially weighted moving average charts. Our learning objectives are to understand when to use X charts, moving average and moving range charts, for monitoring and controlling slow-moving data. We want to be able to calculate the 3 sigma control limits and construct and interpret the data in these charts, and to understand their limitations compared to our standard X bar and R charts that we learned before. We also want to be able to explain what an exponentially weighted moving average, or EWMA, chart is and how it is constructed. So recall that in order to use the X bar and R charts that we did before, we need to have 4 or 5 sample units from the process so that the measurements from them can be used to calculate our X bar, our sample average, and our range. These sample units must be taken then almost at the same time. These need to represent the condition of the process at the time the sample is taken. But the problem is, in many situations, it may not be possible to take such multiple sample units at the same time, or even in quick succession. Chemical processes are examples of such slow-moving processes in which production cycle times are very, very long, and the analysis and reporting of sample measurements takes a lot of time. So the simplest approach in such a situation is to simply plot the individual values that are measured against the control limits. And these would be then control limits that are calculated for those individual values. No longer plotting a sample, but individual values of X. And these charts are normally used along with a chart for successive differences with a subgroup size of n. And these are called the control charts for individuals, or an X chart, and the moving range, or MR. And these limits then, as before, can be calculated using the first, say, 20, 25 observations, sample data, from a process that is known to be already fairly stable. So here's an example. This is actually from our book. It's talking about sand core strengths. Sand cores are used in foundries when you're making shapes out of molten metal. And what they need to do then is they need to take these cores and they need to stress them to measure then the strength of the cores. And there's 3 core types, B, C, and R. And so they want to measure these core types, and they're measuring them apparently every half an hour, starting from 11:15 p.m. And there's 2 measurements, so sample size of 2, not great, but for each one of these measurements. So for example, B, you get 2 measurements at 11:15 p.m., 22 and 15.5, then 11:45 you get 17.9, 22.5, and you can plot these on a chart. So every half an hour you get a sample average and a sample range. Admittedly, sample size only n equals 2, but it's a small sample. But what happens at 3 a.m.? Well, you don't know. When you stress these sand cores, they break, so you can't use them. So maybe they had a delivery problem. But in any case, they decided that they could only take 1 measurement from 3 a.m. And so what do? You can't calculate an X bar anymore. You've got only these individual values of X. So this is where we would use our control chart for individuals, and we would then calculate a moving range between each successive value. So if we're doing this, you would then calculate control limits, as we said, using the first 20, 25 observations. The moving range will track the variability, and your X chart will track the process mean. And you would calculate the control limits as we have seen here. So for the first 20, 25 observations, you would get an overall X bar. Again, it's not the average of sample averages, it's the average, just X bar, for all of these values. And then you're going to have plus or minus 3 sigma levels, where this R bar over D2 is going to be your average over all these different moving ranges. Is an estimate here, an estimate for your process sigma. And so likewise, you use the same idea as our original charts. We'll have an R bar value, this average moving range that we've had, and we have then D4 and D3, but here n equals 2. We use our constants for the n equals 2 because we're just taking the difference between the current value and the previous value. So these would be your control chart limits, but there's many cases you're going to have also standards given. So for example, you're given where the mean is expected to be and what the variation is expected to be currently for the stable process, and then you can actually use those. We didn't do this before, but do this here. We can use that where we know the process should be running, what its variability is. We have simply then plus or minus 3 sigma level control chart limits, and likewise for the moving range chart. Again, we're using the n equals 2 values, but we're going to calculate then, we're going to here estimate the R bar value is going to be equal then to D2 times sigma naught, where sigma naught then is our standard. So let's look at an example of this. What we have here is data points, and again, individual data points, not sample averages. First 20 observations, so 1 to 20, where we know the process is centered with a mean of 10 and a standard deviation of 1. Now, after the first 20 observations, so for 21 to 40, we know there's been a process mean change of 1.5 sigma. So the mean is now at 11.5. Sigma hasn't changed. The variability is still the same, standard deviation of 1. So now we only have one measurement, as we just said, per observation. And we're going to use these first 20 measurements to calculate the control limits. So let's prepare a control chart for individuals and see how well this control chart responds to this change that we know has occurred. So going back to our control limits, this time we have the standards, t equals 10 and sigma naught equals 1. So we have our 10 plus 3 sigma, get 13 and 7 with a center line at 10. For the MR chart, n equals 2, remember, so our sigma naught is 1. So here we are, the sigma naught is 1, and the D value, so we have 3686 is here for our D2 value, and here we have the 1128 for the little d2 value, and then our d1 value was 0. So these are from the equations I had on the previous slide. We're not focusing so much on calculating the control limits. We've done that for the X bar and the R charts. We expect you to be able to do that. Here, we're not going to ask you to do that again, but to make you aware that you're not using the same equations. And of course, normally your statistical program would do that for you anyway. But here, what we have then, 13 and 7 as our upper control limit and our lower control limit for the X chart. For the MR chart, we have 3.686, center line at 1.128, and lower control limit at 0. So let's look at the X chart. Here we have the 13. Here we meet at 10, center line at 10. Center line maybe, and the lower control limit at 0. Oh, I'm sorry, that's wrong. This should be 7. That's a mistake. And then for the moving range, you see the 3.686, 1.128, and the 0 there. So what we see for these first 20 observations, so here and here, we have the mu is equal to 10, and the sigma is equal to 1.0. 1.0. And for these next 20 observations here, the mean has shifted to 11.5. There's been no change in the sigma. And what we see is that this starts to go out of control at sample 36. It's actually kind of borderline, but you could say that you're detecting something at sample 36, which is 16 observations from the time that the change occurred. So What this means is that the X charts are not so powerful. Why? Because the individual values have a lot of variability compared to the average values. It's difficult to see signals in the presence of noise. And also the performance of the X chart is very sensitive to deviation of the process distribution from normal. The X values don't have the robustness present in the X bar values, which you have from the central limit theorem. Remember, the central limit theorem was telling us that, as n, the sample size, gets large enough, then the entire distribution will approach a normal distribution with the same mean and the variance divided by n, the original variance divided by n. And so no matter what, or no matter how your individual variable was distributed, it will become the sample averages, the X bar values will become normally distributed as the n gets large enough. However, there are some clear advantages to these charts. First of all, they're simple. I mean, you're not dealing with X bar for samples, you're not dealing with ranges for samples, you're just plotting the values and plotting the successive differences. Very, very easy. And you can put the specification limit, so USL and LSL. So, don't forget, whenever we've been doing these charts, we've been plotting, so we've got a center line, an upper control limit, and a lower control limit. Now, we're always going to do that. We still need our control limits. The control limits are set up based on the process, the stable process, and then we're using the control limits to control the process. We're using it to see if we're starting to move off where we expect to be or where we should be. But you could put your spec limits on it. I mean, you could just simply, maybe your spec limits look like, maybe they're a little bit tighter. I can change my color here, hang on. I put it in blue. I can have my upper spec limit and my lower spec limit. And so, my points may be looking like this, and maybe I get one here. It's not out of control, but it's out of spec. So you can very easily understand that. You are not able to put these on the X bar chart. I'm not crossing them out here because this is the X chart. It's fine. But for an X bar chart, you can't put in those specification limits onto the charts. They don't have a meaning for a sample average. So that then gives us the overview of the control charts for individuals, or X charts. And next we're going to look at another option for slow-moving processes, the moving average and the moving range charts.